Welcome, curious minds, to another deep dive. Have you ever looked at a soaring skyscraper, a complex bridge, or even just, a new home, and wondered, how on earth did they know how much that was going to cost?
Yeah,
It's a question that underpins every single construction project on the planet, often with billions of dollars and years of effort hanging in the balance.
exactly. Every structure, from the pyramids of Giza to the most sophisticated modern data centers, begins not with a shovel, but with an estimate.
Right.
It's the silent, often unseen foundation upon which entire projects are built, dictating feasibility, budget, and ultimately, whether a vision can become reality.
Today, we're taking a deep dive into the fascinating, intricate world of construction estimating. We'll uncover the history of measuring and pricing construction, from the earliest stonemasons to modern, sophisticated cost databases like RS Means. We'll explore the sophisticated tools and meticulous methods estimators use today, understand the real-world consequences when those estimates go spectacularly wrong. Think projects like the Sydney Opera House or Boston's Big Dig.
Oh yeah, those are classic examples.
And even peer into a future where artificial intelligence and predictive analytics are set to fundamentally redefine how we count the costs.
Our mission for you today is, well, to give you a comprehensive understanding of this critical field. We want to take you on a journey from the meticulous calculations of antiquity to the integrated digital models of tomorrow,
Mm-hmm.
so you can truly appreciate the immense complexity, the strategic importance, and the often overlooked art and science behind accurate cost forecasting in construction. It's about moving beyond the superficial number, and understanding the intricate ecosystem that generates it.
The genesis of guesses, from
Yeah.
stonemasons to structured planning.
Okay, let's unpack this. When we talk about counting costs, we often immediately think of modern spreadsheets, advanced software, vast databases.
Sure.
But long before any of that, even before blueprints as we know them, how did ancient builders figure out what was needed and, more importantly, what it would take to construct their monumental works? I mean, how did the Romans build an aqueduct without a detailed estimate?
It's a profound question, and what's truly fascinating here is how far back the practice of detailed measurement and specification actually goes. We can trace the roots directly to figures like Vitruvius.
Vitruvius.
Yeah, his 10 books on architecture offer incredible, almost forensic insight into how construction was conceptualized and executed in the Roman Empire. He wasn't just a theoretician, he was detailing practical, replicable methods that implicitly drove early forms of, let's call it, cost engineering.
So Vitruvius wasn't just talking about grand designs or aesthetics. He was delving deep into the nitty-gritty of material science and application, almost like an early version of a modern specification writer. Can you get some specifics from his writings? I'm particularly interested in these ancient material recipes.
Absolutely. Imagine having to specify the exact mix for mortar, which is the literal glue holding structures together without, modern chemical analyses or standardized engineering codes.
Right, no ASTM standards back then.
Exactly. Vitruvius meticulously details this for you. If using common pit sand, the ratio is 3 parts sand to 1 part lime. But if you're using river or sea sand, which have different properties due, he says, to having been washed clean by the waves, it shifts.
Okay.
It becomes 2 parts sand to 1 part lime, with an added crucial instruction to include a third part of pounded and sifted burnt brick for a better, more durable composition. These weren't mere suggestions. They were precise, almost prescriptive formulas.
That's astonishing. He wasn't simply saying, use good mortar, but providing a formula that varied based on local material availability. That level of detail must have been revolutionary for ensuring consistent quality across different projects and regions.
It truly was. And the precision didn't stop at basic mortar. Even for more complex finishing applications like stucco,
Yeah.
the detail is remarkable.
Sacco, how so?
Vitruvius describes a multi-coat process, starting with a very rough rendering coat, followed by layers of sand mortar, then a second and third coat, all building up to about 58-inch or 16 millimeters of thickness. This wasn't just about creating a smooth or decorative finish. It was fundamentally about ensuring strength, weather resistance, and durability. Crucially, each of these multi-step processes, each layer, implied a specific cost in terms of material quantity, preparation time, and skilled labor input.
So every step in these detailed instructions, from the type of sand to the number of stucco layers, had an embedded cost and labor component. It makes you realize that even in antiquity, builders were essentially performing a rudimentary form of quantity takeoff and unit cost application, even if they didn't call it that.
Precisely. And beyond materials, Vitruvius also provided precise rules for proportions and dimensions, from ionic column bases, which had a height equal to half the thickness of a column and the same for their projection,
Very specific.
to the dimensions of atriums, like recommending the tablinum, the master's office, be 2/3 the width of a 20-foot atrium. These weren't arbitrary aesthetic guidelines. They were fundamental to calculating the required quantities of stone, timber, or other materials, ensuring structural integrity, and, facilitating the early stages of resource allocation.
Right.
The true insight here is that by codifying these recipes and dimensions, Vitruvius provided a repeatable, scalable framework. This allowed Roman builders, even without modern accounting, to consistently predict resource allocation and quality, transforming monumental undertakings from artistic endeavors into manageable, kind of estimable projects.
So even back then, the emphasis was on meticulous detail and specific material use, which allowed for a very early, perhaps implicit form of cost projection and consistency. But what about the really big stuff? Lifting colossal stones for temples or monuments. That must have been a huge labor cost factor.
Absolutely. Beyond just materials, there were also detailed methods for executing tasks, especially those involving colossal loads. Vitruvius describes systems for lifting heavy objects, from simple windlasses to complex axle trees with large drums.
Like cranes.
Essentially, yeah, sophisticated ancient hoisting machines. The Greeks called them diastis or epidakion. These involved complex block and tackle systems with double rows of sheaves and specialized rope passing.
Okay.
This highlights an early understanding of labor productivity and mechanical advantage for large-scale tasks. The insight here is that they consciously developed technologies and methodologies to reduce the sheer human effort and thus the cost of heavy lifting.
Yeah.
It wasn't brute force, it was applied engineering aimed at efficiency.
That's truly fascinating. We've seen how ancient ingenuity laid the groundwork for quantification and early resource management. But as the world sped up and structures grew from temples and aqueducts to entire cities and global infrastructure, the challenge of counting the costs demanded a revolution in how projects were defined and priced. So how did these artisanal methods evolve into the rigorous, standardized approaches of the modern era?
That's a crucial pivot in our story. If we connect this to the bigger picture, the need for standardized ways to describe, measure, and then price construction work became paramount as projects grew exponentially in scale, complexity, and geographical dispersion. The days of a single master builder overseeing everything with a known team were fading.
Right.
The fundamental challenge you see is that construction is bought before it's manufactured.
That's a great way to put it.
Yeah. Unlike purchasing a manufactured product, you can inspect beforehand, say, a car or a television. You're relying entirely on drawings, detailed work descriptors, and a promise of future performance. This inherent intangibility makes the initial cost prediction a greater challenge, demanding meticulous planning and a common, unambiguous language to define the scope and quality of work.
So it's about clearly communicating exactly what needs to be built and to what standard to someone who hasn't built it yet. This leads us directly to the bedrock of modern construction.
Yeah.
Contract documents, right?
Precisely. These documents become the legally binding Bible for the project. The construction drawings are what define the quantity of the work, the lengths, widths, areas, and volumes of every structural element, every finish, every pipe.
Got it. The what and how much.
Exactly. Then the project manual, which includes the specifications, meticulously defines the quality, the type of materials, their performance requirements, installation methods, finishes.
The how well.
You got it. Both are absolutely critical for an accurate estimate, and experienced contractors know they must perform a deep dive into these before even thinking about submitting a bid. Misinterpretations or omissions at this stage are not just errors, they're financial landmines waiting to explode later.
Here's where it gets really interesting. That's a massive amount of information. How did the industry standardize this avalanche of data to make it universally understandable and comparable for estimating, especially across different firms and regions?
That's where systems like CSI Master Format came into play, a true game changer in how construction information is organized. This became a key standard for organizing these specifications and, by extension, the cost estimates themselves.
Raster format, okay.
It categorizes construction into divisions like Division 07 for thermal and moisture protection, 08 for openings, windows, doors, 09 for finishes, paint, flooring, 22 for plumbing, 23 for HVAC, 26 for electrical, among many others.
So it's like a universal library Dewey Decimal System, but for construction components.
That's a great analogy, yeah. This structured breakdown helps dissect an incredibly complex project into manageable, estimable components, ensuring that every element, from the specific type of insulation to the window glazing system or the roofing material, has a designated, universally understood place for its specification and associated cost. It essentially created a common language for capital, allowing diverse teams to communicate costs effectively.
So the shift was from individual artisans applying known recipes to a formalized industry-wide system of detailing, quantifying, and categorizing every single aspect of a build. This created a shared lexicon, a common language that made large-scale collaborative construction projects truly possible.
Exactly. It's about moving from implicit, experience-based knowledge to explicit, shared, and standardized information. This transformation was essential for the growth of the construction industry as we know it today, allowing for comparative bidding, clearer risk assessment, and a more structured approach to project management.
The benchmark in estimating understanding RS means and its purpose.
Okay, so with this drive for standardization and the creation of systems like master format, how did specific tools emerge to help compile and normalize all these costs, especially when a project is just, a glimmer in the eye? And what role does a name like RS Means play in this complex, often opaque process? I hear that name come up constantly in construction circles.
Yeah, you definitely do. RS Means Company, now part of Gordian, provides widely recognized standard references for construction cost data, and it serves a very specific, absolutely vital function in the early conceptual stages of a project.
Early stages, okay.
Its primary purpose and application are for preliminary cost projections and conceptual estimates. Think of it as a sophisticated, constantly updated benchmark, a guide you turn to when you're still sketching out the broad strokes of a project, during what we call the schematic or budgetary phase, when detailed design data simply isn't yet available.
Right.
You might have a general idea of building size and function, but no detailed drawings to measure from yet.
So, if you're an owner or a designer with a vision for a new building, say a new school or a hospital, you can turn to RS Means to get a ballpark figure, a general idea of what it might cost per square foot for a building of that type in a particular region. It helps you get your arms around the financial feasibility before investing heavily in design.
Precisely. It provides a credible starting point for financial discussions.
Hmm.
However, and this is a critical distinction, the figures developed from such references are of limited use for project control once actual construction is underway.
Limited use. Okay, why is that?
Because they're averages, right? Their application should ideally be discontinued, or at least significantly diminished, as soon as more specific design data becomes available. As the project evolves from a high-level concept to detailed drawings and specifications, the need for more granular project-specific cost information, often derived from actual subcontractor bids and material quotes, completely supersedes the general averages provided by RS Means.
So it's a powerful and indispensable tool for initial budgeting and setting expectations, but it's not the detailed financial roadmap for the day-to-day management of costs during construction. It's like a powerful telescope for planning a journey to the moon, but not the navigation system you use once you're actually there.
That's a perfect analogy. It helps establish a baseline when you're still defining the project, aligning the initial vision with the realistic cost expectation. Project justification, for instance, is inherently tied to a business need and requires a cost-benefit analysis alongside a set of assumptions about market conditions and future value. RS Means data helps frame that initial investment discussion, giving stakeholders a credible, defensible benchmark for what they might be getting into. The critical insight here is that while RS Means is a fantastic compass for setting direction, it becomes a liability if treated as a GPS for the entire journey. Relying on general averages when granular, project-specific data is available is a common pitfall that can fatally undermine a bid or budget.
That makes perfect sense. It's about using the right tool for the right stage of the project. Now let's zoom out a bit. When we talk about the cost of construction, what are the layers that truly go into a comprehensive construction estimate, beyond just the raw cost of materials? It sounds like a lot more than just the price of bricks and mortar.
Indeed, it's far more complex than just a materials list. A robust estimate includes a wide array of factors, meticulously broken down into direct costs, indirect costs, and then further considerations like contingencies, bonds, and subcontractor quotes.
Okay, let's start with direct costs.
For direct costs, these are expenditures directly attributable to physically creating the structure. This includes the actual price of materials, which factors in sales tax, shipping costs, and crucial delivery charges. Getting a specialized beam to a remote site costs significantly more than to a city center.
Sure, logistics matter.
Big time. Then there's labor, encompassing not just basic wages and benefits, but, crucially, the productivity of the workforce. How much work can they actually accomplish in a given time frame? And finally, equipment, which accounts for rental or ownership costs, fuel, maintenance, and operator wages, for everything from excavators to forklifts.
So that's everything directly attributable to putting the building together, the visible components. But what about the hidden costs, the things that aren't physically part of the structure, but are absolutely essential for the project to function and succeed?
Those fall under indirect costs, often referred to as general conditions or general requirements.
General conditions, right?
These are expenditures that don't directly produce the final work, but are indispensable for the project to run smoothly and safely. This can include anything from added utility costs for the site, power, water, internet for the site office, to temporary equipment rentals for things like generators or portable toilets, the cost of small hand tools, or even the significant expense of setting up, maintaining, and removing extensive scaffolding systems.
Scaffolding can be huge.
Well, yeah. It also accounts for mitigating challenges like winter conditions, which might require temporary heating, specialized temporary enclosures, or snow removal. We also include costs for additional copies of plans and specifications, security, safety personnel, and project management staff salaries that aren't directly tied to a specific trade. These costs might seem minor individually, but they accumulate significantly over the project lifecycle and can easily represent, 5–15% of the total project cost.
Wow, 5 to 15%. That's substantial. And beyond those operational costs, what about protecting against the inevitable unknown and financial risks that can plague any construction project, especially long-term ones?
This brings us to contingencies and reserves, which are often confused but serve distinct purposes. A contingency is a deliberate amount of money specifically reserved by the owner to pay for unforeseen changes or cost increases that crop up during a project. These are the unknown unknowns.
The surprises.
The surprises, exactly. Then there's reserve analysis, an analytical technique used to evaluate the amount of identified risk on the project and ensure there's enough schedule and budget reserve for those known unknowns.
Ah, okay. So risks you can actually anticipate may be happening.
Precisely. For instance, if you've identified a 20% chance of needing to remediate a specific soil type based on preliminary tests, you'd budget a reserve for that specific quantified risk. So contingencies are for the unexpected, while reserves are for risks you've identified and tried to quantify.
So contingencies are for the unknown unknowns that might crop up, while reserves are for the known unknowns, the risks we've identified and quantified. It's about building different layers of financial resilience.
Exactly. It's about building in deliberate financial buffers to account for the inherent uncertainties in construction. Then there are bonds and insurance, which are crucial financial instruments.
Bonds, right, like performance bonds.
This includes bid bonds, which protect the owner if a selected contractor fails to enter into a contract. Performance bonds protect the owner against a contractor defaulting on completing the project, ensuring the work will still be finished. And payment bonds protect against a prime contractor failing to pay subcontractors or vendors.
Okay.
From the bonding company's perspective, a bid bond often acts as a lead parachute, indicating that if the contract is awarded, they'll likely issue the performance and payment bonds as well, suggesting a certain level of vetting has already occurred.
So the bid bond serves as an indicator of a contractor's financial stability and a signal to the surety for future bonding. That's quite insightful.
Indeed, it demonstrates a contractor's pre-qualification. And finally, for specific parts of the project, prime contractors rely heavily on subcontractor and vendor quotations. These are specific, legally binding quotes from specialized subcontractors for areas like electrical, HVAC, roofing, or finishes, and from vendors for specific materials like custom windows or specialized steel.
So they replace the RS means numbers with real quotes.
Exactly. The prime contractor meticulously collects and integrates these specific quotes into their overall bid, replacing the more general figures from resources like RS means as the project design solidifies.
It sounds like a complex financial ecosystem where every detail, even seemingly minor ones like the setup of temporary site offices or scaffolding, needs to be meticulously accounted for, then protected against foreseen and unforeseen circumstances through layers of financial instruments. It's an incredible amount of detail just to get to that initial number.
It really is. It's a massive undertaking.
The estimator's toolkit crafting accurate projections.
Now that we understand all the myriad elements that can go into an estimate, How do estimators actually take these raw components, all the materials, labor, equipment, and indirect costs, and meticulously assemble them into a cohesive, reliable cost projection? It seems like a monumental, almost Herculean task to synthesize so much data.
It truly is. It's an iterative, multifaceted process that blends rigorous, detailed analysis with a significant amount of experienced judgment. The first step is typically breaking down the work. Estimators divide the entire project into smaller, manageable activities, often aligning these with the CSI master format divisions we discussed earlier.
Right, those divisions like concrete,
That's
masonry.
exactly. This segmentation allows them to attack the project in bite-sized pieces, making it much easier to assign specific costs and track progress. For example, instead of estimating the whole building, they might estimate Division O3, concrete, then Division O4, masonry, and so forth, down to individual tasks like installing 8-inch CMU walls.
That makes perfect sense. You can't price a whole skyscraper at once, but you can price the concrete for the foundation, then the steel for the frame, then the drywall, and so on, building it up piece by piece.
Exactly. Once the work is broken down, the next critical step is quantity takeoffs.
Takeoffs. Heard that term a lot. What does it involve?
It involves meticulously defining the quantity of the work directly from the construction drawings, literally measuring every single component. This means calculating the length of linear elements like pipe or studs, the widths and areas of surfaces like flooring or paint, and the volumes of materials like concrete or excavation spoil.
So counting everything.
Counting and measuring everything. And here, consistency is paramount. For example, when calculating formwork for a 4-foot-high foundation wall with a total length of 8 feet,
Okay.
the team needs to agree whether to report 64 square feet, 32 feet on each side, or 32 square feet of contact area.
Ah, I see. Different ways to measure the same thing.
Right. It doesn't matter so much which system is used as long as the same method is applied consistently across the entire project and the corresponding unit costs are aligned. This prevents errors when applying those unit costs because a unit cost for formwork per square foot of contact area will be different from formwork per square foot of wall surface,
Got it. So it's about making sure everyone is speaking the same precise measurement language down to the granular detail. Once they have these exact quantities, how do they translate them into actual dollar figures?
That's where unit cost application comes in.
Okay.
Once quantities are precisely known, the estimator applies unit cost, the cost per square foot, linear foot, cubic yard, and so on for materials, labor, and equipment.
Okay.
This is where standardized data, like the kind initially referenced from RS means for early estimates, or more commonly specific legally binding subcontractor quotations for specialty work, come into play. But a crucial and often highly variable component here is labor productivity.
Ah, productivity. That seems hard to nail down.
It is. How quickly and efficiently workers perform tasks directly impacts the cost. Tools like the linear scheduling method, or LSM, it has a long history in Europe as the cyclogram, formalized in the US in the 1980s, can be used for project control.
LSM. How does that work?
In LSM, the slope of an activity line on a 2-axis graph, work amount over time, is directly proportional to its productivity. A steep line means high productivity, a flat line means low productivity.
So if that line is steep, it means they're getting a lot done quickly, reflecting high productivity and therefore lower labor costs per unit of work.
Exactly. And complementing this, lean principles like the last planner system, or LPS, are designed to directly improve labor productivity by ensuring that before a crew even starts a task. It's meticulously defined, all necessary materials are on site, the sequence is logical, and the task is sized to the performer's capabilities. This isn't just about doing the work, it's about enabling consistent high productivity by proactively removing roadblocks and waste, which is gold for accurate cost forecasting. It significantly reduces the variability in labor costs.
That's a huge factor because human efficiency and the conditions workers face aren't always a constant. Given all these variables and the inherent unpredictability of construction from weather delays to material shortages, how do estimators and project managers build in flexibility for the unforeseen, especially in a long-term project? It feels like you need a crystal ball sometimes.
This raises an important question. How do you account for a future that isn't perfectly predictable? Well, you can't have a crystal ball, but you build in several crucial mechanisms to account for risk, uncertainty, and the inevitable changes that occur during a project's life cycle.
Okay, like what?
Firstly, as we mentioned, there are contingencies. These are funds specifically set aside for unknown or unforeseen changes, the unknown unknowns. It's a deliberate financial buffer, a recognition that not everything can be predicted upfront, no matter how meticulous the planning. It's not a slush fund, but a strategic provision for legitimate surprises.
So it's not just hoping for the best, but actively planning financially for the unexpected.
Exactly. Complementing that is reserve analysis, an analytical technique used to rigorously evaluate the amount of identified project risk and ensure there's enough schedule and budget reserve for those remaining risks, the known unknowns. This helps to reduce overall project risk to an acceptable level.
Got it. Contingency for surprises, reserves for known risks.
You got it. Then there's rolling wave planning, an iterative planning method particularly useful for long or complex projects. Near-term work is planned in exquisite detail, while future work is planned at a higher, less detailed level.
So you don't plan the final details too far out.
Right. This allows for adaptability as more information becomes available and the project progresses, preventing premature overcommitment to details that might change.
That makes a lot of sense, especially for long, complex projects where you can't possibly foresee every detail years in advance or where conditions might shift significantly over time.
Indeed. Another key mechanism is constructability reviews. This process involves meticulously evaluating construction documents for clarity, consistency, completeness, and ease of construction before a shovel even hits the ground.
Like a reality check on the design.
Pretty much. It's about identifying potential problems that could lead to cost overruns, like a design that's technically feasible but incredibly difficult or expensive to build early on. Project managers often prepare independent check estimates to verify that designers' estimates are within budget and to proactively promote constructability, essentially having a second, experienced pair of eyes on the cost implications of the design.
That sounds crucial.
And finally, project governance provides the overarching framework, functions, and processes that guide all project management activities to meet organizational goals, including robust cost control. Project management offices, or PMOs, play a vital role here, providing consistent guidelines, templates, and training to support uniformity and best practices in project delivery and cost management across an organization's portfolio.
It sounds like a sophisticated dance between detailed upfront planning and strategic flexibility, all aimed at creating the most accurate financial picture possible while proactively preparing for the inevitable shifts and turns. This truly is a comprehensive toolkit designed to manage uncertainty.
It has to be. The stakes are too high otherwise.
The high cost of miscalculation when estimates fall short.
Even with all these sophisticated tools, meticulous planning, and layers of contingencies, estimates can and do go wrong. And when they do, the consequences can be absolutely severe. We often hear about monumental projects going wildly over budget. The Sydney Opera House comes to mind, or Boston's Big Dig, legendary examples of cost overruns.
Absolutely. Textbook cases.
But what are the underlying, often systemic reasons when these carefully crafted estimates fall so dramatically short?
That's a critical question, and it highlights why construction is often called a risky business. Inaccurate estimates don't just affect the bottom line. They can derail entire projects, tarnish reputations, lead to legal battles, and have lasting negative impacts on all stakeholders. Our sources highlight several key areas where things often go awry. One significant and frequently discussed pitfall is what we call low bid syndrome.
Low bid syndrome, okay.
Under the traditional design bid build method, where contractors compete primarily on price, the lowest bid usually gets accepted. However, experienced estimators are cautioned to be extremely wary of bids that are too low, bids that are significantly below the average or the next closest competitor.
Why is too low a red flag? Isn't cheaper better?
Not always in construction. A suspiciously low bid should immediately activate a red flag for the estimator. It can signal a genuine error or a serious miscalculation on the subcontractor's part, or perhaps a deliberate omission of work scope. Maybe they missed something, maybe they're desperate for work.
Right.
So it's not always a good thing to get the cheapest price. The seasoned prime contractor will often present a detailed analysis explaining why a particular bid might be unrealistically low. Perhaps it misses a key scope item, assumes an impossible schedule, or doesn't account for specific site challenges. They'll emphasize the long-term risk. If the prime contractor accepts such a low bid, and that subcontractor later defaults, walks off the job, or simply cannot perform the work at the quoted price, the prime contractor is left to cover the difference. This difference can often exceed the next lowest bid, meaning the project ends up costing more, often with significant delays.
So it backfires. Penny wise, pound foolish, like you said.
Exactly. Another major issue is inadequate plans and specifications. Owner concerns frequently include cost overruns directly attributable to less than adequate plans and specifications. Design errors, omissions, or ambiguities, if not reported promptly by the contractor, can lead to costly rework, delays, or significant changes later in the project.
Right. Garbage in, garbage out.
Pretty much. The contract documents, after all, are the primary medium through which the architect or engineer communicates design intent, and their clarity and completeness are absolutely paramount for an accurate estimate.
So a meticulously prepared estimate is only as good as the documents it's based on. If the foundation is shaky, the estimate will be too.
Exactly. And then there's the inherent uncertainty and complexity of projects. A project rarely performs exactly as initially planned due to a myriad of internal and external factors, such as new requirements, unexpected site issues, or evolving stakeholder influences.
Things change.
Constantly. In complex environments, uncertainty and ambiguity can blur causal relationships, making it incredibly difficult to define probabilities and impacts accurately, which inevitably leads to increased complexity and cost. For example, an unexpected court decision impacting environmental regulations for an infrastructure project during execution could force major design changes and significant cost increases. The project environment is rarely static.
That's a great point. External factors are often completely out of the project team's control. What about technological innovation? We usually think of new tech as a good thing, leading to efficiency. Can it also contribute to cost overruns?
While certainly beneficial and often a driver of long-term efficiency, technological innovation itself can also cause disruption and contribute to complexity in the short term. Well, if the associated uncertainties of adopting new technology, how it will be integrated, its real-world performance, the learning curve for the workforce are not clearly defined and rigorously managed, it can lead to increased complexity, unexpected issues, and ultimately higher project costs. It's a double-edged sword. Great potential, but also new risks if not thoroughly understood and implemented.
Okay, that makes sense. So it's not just the initial financial number that determines success, but how a project is managed when things inevitably change that really impacts the final cost. How do these changes manifest in actual cost impacts during construction?
Changes are in fact a constant in construction, almost a certainty, and how they are handled directly impacts the final cost, schedule, and quality. The primary mechanism for adjusting costs mid-project are change orders.
Change orders, the bane of many projects.
Can be. They are formal, written agreements or directives representing additions, deletions, or revisions to the original contract documents. They identify the change in scope, the resulting change in price, and any adjustment to the project schedule. A common point of confusion here often arises regarding the authority to authorize work versus the authority to approve costs.
So someone in the field might say go ahead, but doesn't have the power to approve the extra cost.
Exactly. It's crucial that any extra work is authorized and approved by the appropriate parties in the owners' and contractors' offices, not just in the field, to avoid payment disputes later.
So a formal, transparent process is absolutely essential to avoid chaos and financial disagreement. What specific kinds of changes most frequently lead to these cost increases?
There are several distinct types of cost-impacting changes. We have constructive changes, which are accidental or unintended, for example, correcting a defect or a major ambiguity in the contract drawings or specifications that becomes apparent only during construction. Then there are differing or changed site conditions, which are common sources of disputes, such as encountering unexpected subsurface rock formations or contaminated soil not indicated in the original surveys.
Right, surprises underground.
Always tricky. Suspension of work is another, which can be an explicit, formal order by the owner, or a constructive suspension resulting from owner acts or omissions that cause unreasonable delays to the contractor. And finally, acceleration, where the owner demands an earlier completion date, even while recognizing that justified delays have occurred that would normally warrant an extended completion date.
Okay.
All of these require careful documentation, negotiation, and often a formal change order to determine their cost and schedule impact.
It sounds like even seemingly minor changes can have a cascading effect on the budget and the overall project.
They absolutely can. Delays or changes, regardless of their origin, can significantly increase general conditions costs. For example, extending a project by just a few weeks means longer equipment rentals, additional utility costs for a prolonged site presence, increased insurance premiums, and extended salaries for site management staff and security.
The clock is always ticking financially.
Always. Furthermore, these delays have profound impacts on the contractors themselves, beyond just the project's bottom line. Delayed project completion can prevent them from bidding on new work, tie up their valuable management staff on a stagnant project, negatively affect their bonding capacity for future projects, and even tarnish their reputation in the industry.
Wow, serious ripple effects.
Yeah, all of these factors lead to significant corporate overhead impacts and can cause severe financial strain. When these variances, defects, or risks emerge, project teams should immediately use analytical techniques like root cause analysis to determine the basic underlying cause. This allows for prompt corrective and preventative actions. This detect, correct, analyze, prevent, or DSAP cycle helps to prevent similar errors in the future, fostering continuous improvement in project delivery.
So it's about learning from mistakes, not just fixing them, to build more accurate estimates and control costs better in the future. That's a powerful, proactive concept.
It's essential for long-term success.
The horizon of cost control AI and predictive analytics redefining the future.
So we've journeyed from ancient mortar recipes and basic measurements to sophisticated modern databases and complex risk management. But looking forward, how are emerging technologies like artificial intelligence and predictive analytics shaping the future of cost estimating and project control? It feels like we're on the cusp of something truly transformative that could revolutionize how we build.
We absolutely are. The foundation for this profound transformation and what enables much of the AI and predictive analytics we're seeing is building information modeling, or BIM.
BIM. Okay, I've heard a lot about that.
Yeah, and it's much more than just a fancy 3D model. It's a fundamental paradigm shift in how we manage project information and consequently how we estimate costs.
So BIM isn't just a prettier, more detailed CAD drawing. It's something fundamentally different, a whole new way of looking at a building.
Precisely. A BIM model is a 3D digital representation of a building's physical and functional characteristics, but its true power lies in its ability to capture vital information about the entire building process and all its components in a data-rich environment.
Data-rich.
Think of it as a sophisticated CAD model intrinsically linked to a comprehensive, intelligent database.
Yeah.
You can load nearly any electronic data into a BIM specification data for materials everything from weight, size, color, fire rating, and maintenance schedules to installation instructions, product warranties, and, crucially for our topic, productivity and price information associated with each component.
That's incredible.
Yeah.
It truly sounds like a single source of truth for every conceivable aspect of a building, from its initial design to its ongoing operation.
It absolutely is. This makes BIM a shared knowledge resource for the entire design and build team, fostering unparalleled integration, collaboration, and efficiency. All the physical and functional characteristics of every element of the project are captured in a standardized relational database format, making it easy to share project information seamlessly across disciplines and streamline processes from concept to completion. This vastly reduces errors and miscommunications.
So how does this rich data environment within BIM then translate into more accurate and, more importantly, predictive cost control? How does it help us proactively avoid those expensive miscalculations and unforeseen changes we just talked about?
Well, BIM enables a level of analysis and foresight previously impossible. Designers and engineers can run a variety of studies, simulations, and what-if scenarios in a virtual environment before any physical construction begins.
Like testing it digitally first.
Exactly. This allows them to track impacts on everything from energy efficiency, structural performance, and accessibility, ADA compliance, to spatial relationships, constructability, fabrication lead times, and installation sequences, all of which have direct and significant cost implications.
Okay.
For example, an architect can evaluate how different design choices for a facade, say glass versus precast concrete, affect not only the material quantities, but also the labor hours for installation, the type of equipment needed, and thus the overall cost. AI algorithms can then rapidly process these simulations, identifying optimal solutions or flagging potential cost risks.
That's a game changer. Being able to test countless scenarios virtually before breaking ground must save immense amounts of money and time by catching problems or optimizing designs long before they become expensive physical changes.
Absolutely. The savings are exponential. Furthermore, when construction schedules are tied to the BIM model, it becomes a 4D model, adding the dimension of time.
The 4D.
This allows for dynamic visualization of planned sequences and durations against actual progress, making deviations immediately apparent. This is an incredibly powerful tool for time management and, by extension, cost management. Project managers can use this to identify schedule slippages proactively, understand the ripple effects on subsequent tasks and resources, and address them before they cascade into major delays and cost overruns.
Like watching the building get built on screen against the schedule.
Pretty much, yeah. It enables a very dynamic and visual approach to project control, almost like a living Gantt chart. Moreover, project managers extensively use BIM to facilitate rigorous constructability reviews, ensuring designs are practical, efficient, and cost-effective in the real world.
Right, that check step again.
Yep. They also review estimates prepared by designers using BIM data and prepare independent check estimates to keep projects within budget, effectively leveraging the data-rich model for real-time verification and control. And with AI layered on top, systems can analyze historical project data within BIM, identify patterns, and even predict potential cost overruns based on early project metrics, offering proactive alerts.
Wow, AI predicting problems before they happen.
That's the goal. Beyond the raw data and the advanced models, what management philosophies are essential to truly harness these technologies for superior cost control? It can't just be about the tech itself, can it? That's a vital point. The technology is powerful, but it's only as effective as the people and processes behind it. Complementing the technology are lean principles and a proactive, collaborative approach to risk and quality.
Lean, like in manufacturing.
Exactly. Lean management, for instance, is fundamentally about waste reduction. Lean supply systems in construction specifically aim to achieve on-time delivery of information and materials at the least cost and maximum value by relentlessly minimizing waste. This means reducing unreliable supply chains, avoiding large, expensive inventories that simply absorb variability, and minimizing physical waste on site.
Right.
This directly impacts material costs and labor productivity, ensuring resources are efficiently utilized and not tied up unnecessarily.
So it's about efficiency at every single step, not just the initial estimate, but throughout the entire construction process.
Exactly. And building on that is continuous improvement through root cause analysis. The Detect, Correct, Analyze, Prevent, or DCP cycle helps teams systematically address plan failures, quality defects, and even accidents.
That DCP cycle again.
Yeah, by truly understanding why errors occur, whether in design, scheduling, procurement, or actual construction organizations, can implement targeted countermeasures to prevent reoccurrence, leading to more predictable outcomes and lower overall costs. For example, if an error on a drawing is discovered before fabrication, the immediate correction is to stop using that drawing and issue a corrected version. But the root cause analysis would then dig deeper, perhaps revealing that urgency due to late issuance of vendor data contributed to the error,
Okay.
leading to a countermeasure like incorporating vendors much earlier into the last planner system's collaborative planning sessions.
That's a much more profound way of learning than just fixing the immediate problem. It creates a feedback loop for ongoing systemic improvement.
It creates a self-correcting organism out of the project team. Finally, integrated project delivery, IPD, is another crucial philosophy, often used in conjunction with Lean and BIM. This approach focuses on fostering an effective team culture, making collective sense of the owner's goals and translating them into action, even with evolving objectives. Projects using IPD have shown significant success in meeting or exceeding budget and schedule expectations precisely because it fosters collaboration, transparency, and shared risk-reward among all key stakeholders, owner, designer, and contractor from the very beginning.
So everyone's pulling in the same direction, sharing the risks and rewards.
That's the idea. It's a holistic approach to managing the entire project lifecycle, moving away from adversarial relationships towards a unified team effort focused on optimizing value.
It sounds like the future of counting the costs is less about trying to make a perfect static prediction up front and much more about creating a dynamic, data-rich, intelligent environment that continuously learns, adapts, and minimizes costly surprises throughout the entire project lifecycle, driven by both cutting-edge technology and collaborative management philosophies.
I think that's a very accurate way to put it. Outro.
So, from Vitruvius, meticulously detailing mortar ratios and stucco applications, to today's sophisticated BIM models loaded with every conceivable data point and integrated with AI, our deep dive into construction estimating reveals a relentless, centuries-long pursuit of precision and foresight in building our world.
It's a fascinating journey from rudimentary recipes and experience-based judgments to highly integrated, data-driven systems designed not just to forecast costs, but to actively mitigate risk and optimize value.
Hmm.
The immense complexity, the scale, and the sheer capital investment involved in constructing our built environment demand nothing less than this continuous evolution in how we meticulously count, control, and predict the costs.
And this transformation isn't just for the massive multi-year projects like high-rises or infrastructure, right?
Mhm.
The principles of rigorous planning, data integration, and proactive risk management apply to any construction project, big or small, ultimately benefiting everyone involved, from the owner to the last person on site.
Absolutely. These principles scale. As we move forward, fueled by these advancements in cost control, driven by data and artificial intelligence, the question for you to ponder is, how might these shifts reshape not just what we build,
Right.
but how we decide to build, and even who gets to build in the coming decade, potentially democratizing access to complex construction or enabling entirely new forms of development?
That's a truly profound thought, and one that highlights the ongoing evolution of this critical field. Thank you for joining us on this deep dive into counting the costs.
Yeah.
Until next time, keep digging, keep learning, and stay curious.